LeetCode 560, Subarray Sum Equals K isn't just an interview favorite. It mirrors real-world challenges in finance, telemetry, and stream analytics, where tracking running totals is key. Whether it's time series data, real-time dashboards, or smart caching, this problem shows up often. But go in naive and you'll be deep in the quagmire. So how do we go from brute force to blazing speed? Let's wade into the duck pond and find out. Let's kick things off with the brute force method. It's basic, but solid. Time to walk through the code and see how it behaves. First up, we set a counter to track how many subarrays add up to K. Then we loop over each possible starting index. This outer loop anchors the start of every potential subarray. Every time we pick a new start, we reset the sum to 0, clean slate for building a new subarray. We expand the subarray one step at a time by sliding the end index forward. This inner loop tries every combo from the current start. With each new endpoint, we tack on that value to the running total, building the subarray sum as we go. If the sum hits our target K, we count it. This subarray fits the bill. Once we've tested all start-end pairs, we drop the final count, total subarrays that matched our target. This clocks in at big O of n squared time. At 20,000 elements, that's up to 400 million checks. It's space efficient, big O of 1, but for large arrays, it slows to a crawl. So how can we skip repeated work? What if we stash some info to avoid recalculating sums? First, we grab the input array length. We'll need it to size our prefix array. We build a prefix sum array that's one slot longer than nums. That extra space lets us cleanly represent the zero-sum prefix. We populate it by cumulatively adding the original elements, setting us up to grab subarray sums instantly with subtraction. Back to our count, let's reinitialize it. We're still tracking how many subarrays hit K. Time to loop through every possible subarray start index. For each start, we scan forward through all possible ends, covering every subarray from that point. We check if the difference between prefix sums at end and start equals K. That tells us whether the subarray in that range adds up correctly. After checking all possible subarrays, we return how many met the target. We're still at big O of n squared, 400 million operations in the worst case. But now, we dodge raw addition by using prefix sums. The trade-off is memory. We use big O of n space, usually fine, but keep it in mind when RAM is tight. This method skips the repeated math, but it still examines every subarray. Let's level up by counting valid subarrays in one clean pass, with prefix frequency tracking. We'll use a HashMap to record how often each prefix sum appears. This gives us constant time lookups for needed complements. Right away, we seed the map with a prefix sum of 0 showing up once. That accounts for subarrays that start from index 0 and sum to K. Then we set up two variables. One tracks the current running sum, the other tracks our total valid subarrays. We scan the array, updating the running sum with each number we pass. Each time, we check if there's a prefix sum such that current sum minus that prefix equals K. If it exists in our map, we've found valid subarrays ending here. We update the map by bumping the count for the current prefix sum, prepping for future checks. Once we've traversed the full array, we return our final count of subarrays matching the target. This approach runs in big O of n, just 20,000 steps for 20,000 elements, much faster. Space is still big O of n due to the map. In interviews or real systems, this method is gold, clean, efficient, and handles edge cases without breaking a sweat. We began with brute force, easy to write, slow to run. Then we trimmed redundancy with prefix sums. But the real leap? Tracking prefix frequencies with a HashMap. That let us scan once and catch every subarray instantly. We turned a quadratic slog into a linear sprint. And in real-world tasks like stream analytics, caching, or log processing, that upgrade is massive. It's not just clever, it's practical. If you're aiming for top tech roles, this is the kind of optimization that stands out. So challenge yourself. Where else could this trick help your code take flight? Keep solving, keep sharpening, and stay in the swim with the smart ducks.